Hello everyone, welcome to my presentation. This presentation is the final task of the Machine Learning Task-Based Internship Program. My name is Maliheh Sefat, and today I'm going to show you some machine learning classification models with Scikit-learn library. The Scikit-learn library is in this process. There are documentations, APIs, datasets, etc. And for good practice, I collected all the necessary libraries and module in the first cell of the notebook. We need a data set to do our machine learning modeling. And sometimes we load the data set from internet, sometimes we have the data set. But for this presentation, I decided to make a classification data set with the make classification method of data set module from Scikit-learn library. I decided on 200 samples with 2 features and 4 classes. With this class separation argument, I wanted a little nonlinearity in the data and the list of weights for distribution of labels are like this: 10%, 20%, 30%, and 40%. And I can show you the scatter plot of the points on the Cartesian plane like this. You see that there's a little nonlinearity in the data. Then we can convert our dataset to a data frame of pandas with this syntax. And to show the head of that data frame, this is the head, and the data is like this. Then we go to explore our data. We need to get an understanding of the structure of the features and the data in general. One way to do so is to use the info method of pandas on the phone. And this info shows that our little data set uses less than 5 kilobytes of memory. There are 200 entries and no null values. The data types are float and integer. So I can get the distribution of flat labels with grouping our data frame on the target column and getting the size. It shows the same distribution, 10%, 20%, etc. Alternatively, I can visualize the same distribution with a count plot of seaborn library. And this is a visualization of the class label. Then there's pre-processing, and pre-processing is a must, even though our data does not have any duplicated rows. You see, it's a duplicated method, and there's no missing value, but we need to do pre-processing anyway. And we can get a statistical description of our data frame with the describe function. I just rounded the digit to 3 decimals. We get the minimum, maximum standard deviation, what is the percent. Now it's time to select some features and do some data splitting. Why do we select features? Because in real-time data, there are many features, not just 2 features. And we need to decide which features are more deterministic, meaning that which features have the most effect on the label. One way to do so is to use a pair plot. When we draw a pair plot of our data, we can see any linear relationship between our features and variables. We can see the distribution and the outliers of usual data, and then we can choose which features are more important in appointing the classes. So here's the pair plot with the hue on the target label. Then we need to split our example. We do the training of the model on some of the data and keep the rest of the data for testing or evaluating our model. Train test split method of the model selection module of Scikit-learn does that. It returns a tuple of X train, X test, Y train, and Y test. I chose the test size to be 30% of all the data, and I did the stratification on Y. The stratification here means that the train test split method returns training and test subsets that have the same proportions of class labels as the input dataset. I can display it with bin count method of NumPy library on the Y train and Y test, and you see that the Y train and Y test have the same proportion of labels as the original Y. Then there's feature scaling. Most machine learning algorithms will work better with standardized or normalized data. Although our data today is pretty much standard, but don't forget standardizing. So we import the standard scalar from pre-processing module of Scikit-learn, make an object of it, name it scalar, and fit that scalar object on the X train. Fitting here means to compute the mean and standard deviation of the data. Then we transform our data to scale data. Now we have X train scale and X test scale. Now we are ready to build our classification model. The first classification model is Perceptron. And Perceptron is the simplest artificial neural network unit that uses input data to make simple binary decisions by applying learn phase and a bias throw and activation function. These x's are the x value input, and this is the w, the weight, and this w0 is the bias. We get the dot production of these and use the net input function to do a summation, and then we filter them through a threshold function to get the predicted label. By comparing the predicted label and the actual label, Perceptron gets the error, and according to that error, updates the weight. This loop continues on and on until the Perceptron converges, and it only converges on perfectly linear data. Here is the Python implementation of Perceptron. We import the Perceptron from linear models of Scikit-learn, make a PPN object of Perceptron with eta learning rate set 10%. We should know that too large learning rates might result in the algorithm, might make the algorithm overshoot the global cost minimum. Cost is the summation of all the errors, and we want it to be minimized to get the most accurate prediction. We use the fit method to fit the model. Now we have a fitted perceptron, and we predict the labels of X test scale with this prediction, with this predict method. When we compare the actual labels and predicted labels on the test set, we can get the number of misclassified examples. Here it is 7. And the accuracy score from the metrics of Scikit-learn can give us the accuracy score, which is 88% in this case. Alternatively, there's a score method in all the machine learning models of Scikit-learn that returns the same accuracy score. Now, there was a very interesting, cool mini program introduced in the book we studied to plot the decision regions. Here's the program. I put it in the plot place module for myself in order to be able to import it wherever I need it. So we stack our explain scale and test scale and y train and y test. Now we have the combined x and y, and we plot decision regimes with that mini program. Here is the result. The decision regions of points trained with Perceptron model. The second machine learning model I'm going to talk about is logistic regression. Logistic regression is similar to Perceptron, except it uses conditional probability that sample belongs to a specific class given its input vector. There's the x vector, input vector, the weights, and the net input function. But this time, logistic regression calculates the probability with the sigmoid function. Sigmoid function is this. It maps any number to the range between 0 and 1. And we use it to get the probabilities and use those probabilities to calculate the cost function. And here how cost works. When the predicted label and the actual label are equal, for example, we have the actual label y and predict y, the cost is 0. And when they differ, the cost increases. So when we have the minimum cost, it means that we have the least error possible. And we minimize this cost function with optimization algorithms. For example, the gradient descent is a good optimization method that calculates the slope of cost functions with respect to each weight and updates the weight to minimize the cost. Here's the implementation of logistic regression. We import it from linear model, make an LR object of that, and there's a C parameter here. C is related to regularization. The smaller C results in a stronger regularization and looser fit. There's a solver argument, which is the optimization function. There are several solvers, and I'm going to talk about that in a moment. We fit our model on the data, get the accuracy score, which is 96% in this case, and we plot the decision regions of the points trained with logistic regression. Here's the result. Now, what is regularization? Regularization is a technique used to prevent overfitting by adding a penalty for larger weight to the model's cost function. And overfitting means that the model captures the patterns in the training data well, but fails to generalize well to unseen data. Here shows how overfitting happens. The model fits perfectly for the training data, but cannot capture unseen data. And they are related to variance and bias. Variance means measures the consistency or variability of the model prediction, and bias measures how far off the predictions are from the correct values in general. High variance is proportional to overfitting, and high bias is proportional to underfitting, and we need a good compromise. We use the parameter C for that. The smaller value of C corresponds to stronger regularization, which can help prevent overfitting by penalizing large coefficients. The third machine learning algorithm is support vector machine. Any point in the mathematics is a vector, and the vector closest to the decision boundary are called support vectors. If we are able to maximize this margin between the support vectors, we can get a good decision boundary, and this is SVN. So we imported SVC from Scikit-learn SVN and we set the kernel to linear for now because our data is pretty much linear. We have the C parameter that is again related to the regularization. The smaller C results in wider margin, but it classifies some training points. Here's the results. We achieve 96% accuracy This is the decision region plot. And here's how C works. The small c can point the bigger margin, wider margin, but misclassify some derived data. And large C overfits on the data and finds a narrow margin. Another thing we can do with SVM is the kernel trick. It is used on nonlinear data and it involves transforming the data into a hyperdimensional space like this. When we have nonlinear data, if we imagine it or map it to a higher dimension, we can find a linear hyperplane to classify it. And when we reverse it back to lower dimensions, we have a nonlinear decision boundary like this. Kernel is a mathematical function that implicitly maps data to a higher dimensional space. So the shape of this decision boundary comes from the kernel. And this is the implementation of kernelized SVM. And this is the high decision regions. You see that now we have a curved decision boundary here. To show it better, I created a nonlinear or linearly inseparable data set with the measurement of data set, Scikit-learn data set. I chose 200 samples with the measurement, and I just created a logistic regression object to fit it. And this is what we get. You see there are two crescents, red crescent, green crescent. We have two moons here, and logistic regression is not able to classify it very good. We get 83% accuracy. So when we use the kernelized SVM and choose a nonlinear kernel, there are several kernels, this is the result. We get a curved decision boundary and we reach almost perfect accuracy, 98% accuracy of classification. The fourth algorithm of machine learning is decision tree. And decision tree works by breaking down the data by making a decision based on asking a series of questions. And the steps are like this. We have the whole data set and we split the data by asking the question on the feature that results in the largest information gain. The information gain is the difference between the impurity of the parent node and the sum of the child node. Impurity. I show how it works on the plot. We import the decision tree classifier from Scikit-learn tree, make an object of it, train it, and choose a function to measure the impurity of each node with the criterion. I set it to Gini, the criterion. There are impurity measures, entropy, classification error, etc. And we get 81% accuracy actually at this time. And this is the decision region. There's a cool method plot tree from the Scikit-learn tree, and it can plot how the tree decided on the label. Here's what has happened in our tree. At the root of our tree, we have node 0, and we have all the data sets, 140 points from the X-train scale, not train. And the Gini impurity is 70%. That means that if we want the class 3, 70% of the data at this node are not class 3, are impure. And the question here is whether feature 1 is less than or equal to this number. If the answer is yes, which is true, the tree goes to this branch. And if the answer is no, which is false, the tree goes to this branch. And the splitting continues until we reach zero impurity, meaning that we have pure classes at the leaf. You see, at the leaves, we have only class 3 or 2 or 1, etc. Random forest classifier model works with combining multiple decision trees and aggregating the predictions by each tree to assign the class label by majority vote. And that's it. We have several trees and we get the majority vote of their decision to reach the final decision. We have the impurity criterion again, and n estimator is the number of the trees. We chose 25 estimators for our random forest and train our forest on the data. And here's the result. It's slightly better than before, than a single tree. The last but not least model is connier's neighbor. It is a lazy learning algorithm. It is not like the previous models. It actually doesn't learn from our data. It memorizes the data, literally memorizes the data, and decides on the label of the unseen data by getting a majority vote or average vote of the nearest neighbor to it. And we need to define a metric for calculating the distance between the lasers. And this is what we get from the KNN, 96% accuracy. Thank you very much for watching my presentation.